Power is defined as the rate of energy transfer with time. So P with a bar at the top there. So this is the average power average because sometimes the power more, sometimes less, or maybe the power is increasing. So we take the average. Okay, bar with the bar there means the average power is the energy or the work done divided by the time taken. So it's W, the work done, divided by delta T. Delta T is the uh, time taken. The unit for power is watt or joule per second. Okay, the whole thing here, joule per second. But the joule per second is 1 watt. Okay, okay, right. This is equation 5.23. Now we look at this work done here, W, W. So the W here can actually be replaced with the force times the distance moved. The force times the distance moved. This one. The W here. You can replace with the force times the distance moved in the direction of the force. Or this is our definition of work done. Okay. So if you substitute this into the equation here, you will get the W you replace with the force times the distance, right? So the delta T remain delta T. But if you look at this delta X over delta T, delta X over delta T is the distance moved divided by the time, and that is the average velocity. So we have another formula for the power. Power is the force multiplied with the velocity. This one. We have two formula. The first one is work divided by time. The second one is the force multiplied with the velocity. Okay. So now we come back to the units. One unit, 1 watt is, that means the power. This is the unit for power. 1 watt is equivalent to 1 joule per second. It is also equivalent to 1 kilogram meter square per second cube. They express this in the base quantity, right? So this one is base quantity. All of them, kilogram, meter, and second, they are all base quantity. Whereas this watt and joule, they are derived quantities. So you can look at it in many different ways. Either watt, joule per second, or kilogram, meter square per second cube. In US, I think not only in US lah, in engineering, they still use this horsepower for power instead of watt. The conversion is 1 horsepower is 746 watt. So this is the conversion. If you look at our aircon, our our aircon at home, they are still using horsepower. So the aircon that we install at home usually 1 horsepower, 1.5 horsepower, or 2 horsepower for one room. Right? So if it's a very big room, then normally we'll install an aircon with 2 horsepower or 1.5 horsepower. Okay, so not only in US, in engineering they still stick to this old units, right? 1 horsepower. Okay, then we look at our unit we use for calculating our Tenaga National Bill. Right? So it's kilowatt hour. Kilowatt hour. That means it is this is the unit for energy. how much is the energy consumption. Now, why I say this is energy? Because this one is actually kilowatt hour is actually the power, right? Power. Better clear all this. My writing is very bad. So this one, kilowatt is actually power. Kilowatt is actually power. And this hour here, this hour here is actually the time. The hour is actually the time. So if you take the power multiply with the time, you're actually calculating the energy, right? So kilowatt hour, it is not power, but it is the energy consumed. So if you take 1 kilowatt, which is 1000 watt, multiply with the time, 1 hour is actually 3600 seconds. So you multiply all this together, you get the answer 3.6 times 10 to the power of 6 joule. So this is the another unit for energy, kilowatt hour. And this one used for our Tenaga national bill, right? Kilowatt hour. Okay, so we're going to look at a problem, and we're going to solve this problem using either one of this formula. Power is the work divided by time, or the average power is the force multiplied with the velocity. It depends on the question, right? Can you read this example 5.12?
A 1 times 10 to the power of 3 negative kg elevator car carries a maximum load of 8 times 10 to the power of 2 kg. A constant frictional force of 4 times 10 to the power of 3 Newton retards its motion upwards as in figure 5.27. What minimum power in kilowatts and in horsepower must the motor deliver to lift the fully loaded elevator car at a constant speed of 3 meters per second?
Okay, right. Let me explain the problem, right? Now, this problem has an elevator. We call this a lift. There they call it elevator car. So never mind. So this is an elevator car, and the mass of this elevator car is 1000 kilogram. 1 times 10 to the power 3. This is 1000 kilogram. So a maximum load of 8 times 10 to the power 2. So this is actually 800 kilogram. So the mass of the elevator is 1000 kilogram. The mass of the load is 800 kilogram. So we have the total mass is actually 1800 kilogram, right? Now this elevator is pull up using the motor, and over here the cable is rubbing against the motor there, and there is a frictional force of 4000 newtons. 4 times 10 to the power 3 is 4000 newtons. Right? What minimum power in kilowatt and in horsepower must the motor deliver to lift the load, the fully loaded elevator car at a constant speed of 3 meter per second? Okay, I want to explain this constant speed of 3 meter per second. Now, when the elevator car is moving with a constant speed, that means it is not accelerating. So there will be no net force. If there is no net force, that means the forces there, they balance one another. Okay, the forces balance one another. So before we how to say before we calculate the power, we have to look at the forces acting. Okay, so the forces acting on this system, they are: number one, the tension in this cable here, the tension. Number 2, the weight, the total weight of the cable car and the passenger, the weight. And these two forces, they are not the only forces, so you cannot say the tension equal to the weight, right? There's another force that is the frictional force. So this frictional force is actually here, somewhere here, rubbing of the motor against the cable. So we have three forces in this system. So because it is moving at a constant velocity, these three forces, they balance one another. The net force is zero. So we're going to look at how they balance one another by looking at the direction. Okay, since the cable is pulling the elevator and the passenger upwards, so the tension in the cable is acting upwards. So the tension is acting upwards. The frictional force is always opposing the direction of motion. So the frictional force is acting downwards. Another force that is acting downward is the weight, the weight of this whole thing, the passenger and the elevator. So these three forces, they balance one another. So by looking at the force diagram, I know that the tension in the cable is equal to the weight and the frictional force. So this is the equation. Okay, now we can only say tension equals to the weight plus the frictional force, provided there is no net force. If there is net force, then this will produce the net force. Right? The tension, you have to minus the weight and the frictional force. Right? So since they are moving with constant velocity, we say they balance one another. Tension is the weight of this cable car, fully loaded cable car, not cable car, cable elevator, elevator car, sorry, elevator car. So what is the weight? Weight is mg, right? Is the mass times the acceleration due to gravity. Mass is how much? 1,800 times this g, that will be the weight. How much is the frictional force? It is given here. The frictional force is 4 times 10 power 3, that is 4,000. So this is the force exerted by the cable to pull the whole thing upwards. So this is the tension. It is also the force used. This is also the force used. If the system is moving at 3 meter per second, 3 meter per second, how much is the power? So which of this formula are we going to use? Which of this formula are we going to use? Power is the work done divided by time, or power is the force multiplied with the velocity. Here we know the force, and we also know what is the velocity. So
Second
we
one,
use number 2, correct. So we use number 2. We use the force exerted by the cable multiply with the velocity it is moving. So it's 21,600 times the velocity, which is 3. So answer is 64,800 watt. So you want to change to kilowatt, you have to divide by 1,000. So it's 64.8 kilowatt. Okay. Now using this conversion factor here, this conversion factor, 746, we can change it to horsepower. So this power here, 64,800. If you want to change to horsepower, 64,800, you divide by 746. So we know the lift is, the power of the lift is 86.9 horsepower. So it is still less than the power of one car. Our car, that the car is normally, I think, around 90. The 1.5 cc is normally around 90 to 100 horsepower. It's only 86, less than that of a 1.5 cc car. Okay, so